Today, we will learn about only one classifier, which is called logistic regression. Are we together? Logistic regression. Now, when people teach, this word has a whole bag of problems associated with it. First of all, the name is a misnomer. It is called logistic regression. So if you look at the name, what does it look like? An algorithm that does what? Regression. But actually, it's not regression. It is actually, this is a classifier. This is the first thing you need to remember, right? So, by the way, this is a very nervous era. People, they always, if you look at the people in the data science community who do interviews, almost everybody has a joke of meeting a candidate who in the list of regressors said linear regression, logistic regression, and so on and so forth, right? So that would not really be a very, well, and they of course point out that logistic regression is a classifier. Well, yes and no. It is a classifier. We'll start about it. But there is actually a generalized way of looking at regression, which I will teach you at some point. I'll do an extra session for you. It's called generalized linear regression, which uses a link function. Should you start thinking about that, then there is a way, then the situation gets a little bit more, let's say, interesting. We'll talk about that later. Go ahead. Premjit, are you asking a question? No. Okay. So this is logistic regression. That is the topic for today. It's a long topic. We are going to cover it in the next 2-3 hours. It's a long theory class and it's a very long lab class. And today I'll really expect you to finish your homeworks if you haven't done that, guys. Huh? So just, but anyway, I'll talk about that at lunch. We'll have a very brief lunch today. So we won't start here. We will get here slowly. But let us craft a problem. We won't use cows and ducks. We will use a little bit more complicated problem, more amiable to this. So I'll create a toy problem. And the biologist and the farmers would laugh at it. So I'm taking a lot of liberties with reality here, but go along with it. The point is to create a toy problem that will help us understand. Suppose we are trying to distinguish between blueberries and cherries, right? So let's say that our axes are weight and size. Two axes. So x1 is weight and x2 is size, right? Size is size. And now let us project the blueberry points. You would agree that blueberries are small. They would be somewhere like this. And I will deliberately oversimplify the situation. Remember, this is a toy example, huh? Motivating example. And then you have strawberries. Oh, no, did I say cherries? Cherries. So let's say cherries. Maybe occasionally. These are our cherries. This is our cherries. And then, of course, some blueberries can be a little bit bigger. And there's some region of overlap. And I ask you, how would you tell an arbitrary point X, is it a blueberry or a strawberry? So let me ask this question. Let's look at point A. There is a fruit whose weight and volume and size puts it here. What would you guess? Is it a blueberry or is it a strawberry? Sorry, a cherry. A, you would definitely call a blueberry. Right? What about B? Cherry. It is definitely a cherry, right? These two are very clear. What about C? So C is likely a blueberry. And what about D? Likely cherry. Now, why is it that you are sure of A, but not of C? A and B you're sure of, and C and D you're not sure of. Rantik?
Because they're close to the kind of outlier, right? On the basis of weight and the size.
No, they're not outliers. Outliers are away from all data points. Yeah. Yeah. See, the moment you look at this data and I ask you to guess the points, what your mind begins to do is it begins to draw imaginary something like this. It is beginning to conceive of is this correct? Right? And it basically says, in your mind, you begin to draw a line like this. And you begin to say, this side is blueberry, right? Let me use the right colors here. You begin to say that in this line, this side is blueberry. And on this side, it is cherry. Isn't it? That's how your mind is deciding, isn't it, when I ask you that? So because A and C fall on the blue side of that, the lower side of this line, you call it a blueberry. The things that fall on the other side of it, you call it a cherry. But you also notice that the further away you are from the decision, by the way, this thing has a name. It is called the decision boundary. And this is a very important term, decision boundary. In fact, it is the crucial term in classifiers, decision boundary. Decision boundary. Would you agree that if I have to create a classifier that tells whether a point is a blueberry or a cherry, the problem is equivalent to finding the decision boundary? Because if you find the decision boundary, then you can tell on one side is blueberries, on the other side is cherries. Do you agree with that point, guys?
Yes.
Isn't it? The problem is equivalent. So to create a successful classifier is the same as to discover geometrically the decision boundary. Right? And so that is a very crucial observation. Remember, the pursuit of a classifier is the pursuit of a decision boundary. In the feature space, in which space? The feature space, data space. Right? So let us find that decision boundary. Now the question is, what is this decision boundary? Some observations associated with decision boundary. The further we are from the decision boundary, the more sure or unsure we are. The more sure we are.
Sure.
Conversely, the closer we are to a decision boundary, the less sure we are, isn't it? Why are we less sure?
It could be both blueberry and a cherry.
Right, because data is not so clear-cut. There's always noise in the data. So there are some blueberries here and there are some strawberries all over the place here, isn't it? So all we know is that if we are sitting on the decision boundary itself, then what happens? What would you say it is? Is it a blueberry or a cherry? Oh, either way. You could go equally either way, isn't it? So the way you would say it probabilistically is that the probability of it being a blueberry probability of a blueberry of that point X, let's say this is X, right? Of that point X of blueberry. So here's the language, the mathematical language. Given point, if we are sitting on the decision boundary at X, right? You say that blueberry probability of blueberry given at the point X, given X, is at this moment 0.5, half, right? Likewise, the probability at that point of cherry given X is also 0.5, 50-50. Would you agree with that? On the other hand, what would you say? Now let's develop our language a little bit more carefully. Much of this math language is very elementary to get. Probability of blueberry at, let me just look at the probability of blueberry, because cherry would be the converse of it, 1 minus blueberry. Would you agree? If the probability of something being a blueberry is 70%, probability of its being strawberry is 25%, right? So this is it. So we go here at point A. Let's go back to point A and see what it was. Look at point A. At point A, what is the what would you say? Probability that it's a blueberry? Almost sure, right? So let us say that it is approximately equal to 1, right? 100% probability, right? At the same time, the probability of its being a blueberry given point B is closer to 0, isn't it? This is the way we write the language. So now let us go this. We will only look at the probability of a blueberry because probability of a cherry is this. What do you observe? What is the mental intuition you have? The distance from that decision boundary, isn't it? Do we agree? Distance from the decision boundary. So now I'm going to use this tiny bit of space. I seem to be going circular in my diagram. Let me take a point. This was a point X. Let me take, actually, let me not call that point X. Let me call that point, just say P. And in my here also, I will change my note because I'm going to use X for something else, guys. I hope I'm not confusing you by changing the name of this point. Oh, probability is P and this is Q. That will be terrible. Let me call it Q. Probability at the point Q. Do we agree? We are still on the same page. Now I'm going to take an arbitrary point X from the origin. Let us say I take this point, this, right? This point given by the vector X. Remember, every point can be represented by a vector X, isn't it? This point. And I ask you intuitively, what is it? You would say, let me do one thing. Let me find the distance of this point from the decision boundary. This is your distance. Distance of X. This is distance from where? The origin? No, it is the distance from the decision boundary. And you can tell, now I'm going to say a statement which is, tell me true. Distance of X greater than 0 means probability of blueberry. Actually, let me change the language. I will look at the probability of instead the cherry because that will align with the language. Cherry is approximately 1, isn't it? If the distance is much greater than 0, means you're really far from the decision boundary in the positive direction. It is this. If the distance is less than 0, means you're far inside, like point A, this point, right? If you're on the lower side of it, distance is negative, right? Because you take one distance to be positive on the upper side, downwards, you take it to be negative distance. So here, you would say that the probability of cherry is, probability of a cherry is what? Close to?
0.
0. It's close to 0, right? So then now let's carry this intuition forward. Let me summarize it, because if you get this intuition, all we have to do is use a little bit of simple mathematics to develop some very elegant formulations. Go ahead, Rantik. Oh, we'll learn that. At this moment, we are purely at the level of intuition, right? In fact, that is what we are going to do at the next time. But so far, you're clear with the intuition, isn't it? What we are saying is we need a decision boundary. It's very intuitive. Geometrically, you can look at it and say classifiers are nothing but machines that discover the decision boundary. Once you have the decision boundary, the only question is how far you are from it. By the way, this is for the linear situation, but also for non-linear situation, it will be true, but in a more complicated way. But okay, distance from the decision boundary matters. The further you are, the more sure you are. The closer you are, the more unsure you are. And if the distance is 0, oh gosh, you're not sure at all, 50-50, right? It's a toss of a coin at that moment. So that is the intuition we'll carry. Now we'll simplify this notation. Mathematicians, see, what we are looking at is probability of a cherry at a point X, isn't it? So we will say, this is what we are looking for. We will simplify the notation to P just X. We'll assume cherry. Are we together? We assume we are talking of cherries, right? We'll just assume. So we'll use this. The reason is that, see, here's the thing. More formally, we should use the notation on the left, but more commonly, people use the notation on the right. In fact, your textbook uses the notation on the right. Huh? So we'll just use that simpler notation. But remember that we're always talking about probability of cherry. Probability of blueberry is just 1 minus probability of cherry. So now let's think about it in terms of one graph in our mind. This is 0. This is D. D is distance from the decision boundary, right? So you realize that when you are really far away, let me take this. When you are really far away, let me say that this value is 0. This value is, this is the probability, P, probability of a point dx. Dx is here. Probability x. What is the maximum probability something can have? 1. So this is 1. This is a 1 value. What is the lowest probability something can have? 0. Okay. So at very large values of D, what is the probability that it will have, that it's a cherry? Pretty high, right? So we can say that it will be like, very, very high here, close to 1. Right? At very negative values of the D, means in the other direction, in the lower direction, if you go very far from if you go back to this, you go very far down compared to the decision boundary, far down from the decision boundary. What is the probability that it's a cherry? It's 0, right? It is 0. So we are here. Now what happens? As you come closer to the decision boundary, at the distance 0, what is the value here? At half, when you're literally sitting, when dx is 0, what is the probability that it is a cherry?
0.5.
0.5.
0.5, right? This is a 0.5. So we know 3 points the answer to. Now what happens? Let's think about it. this probability, rises up, isn't it? And you know that, so first thing is there any distance from the decision boundary where we will not know the answer? No. There'll always be a probability, isn't it? That speaks to the fact that this probability is a continuous function. Is there any reason to believe when you look at this thing that the probability as you go along, as you go in the perpendicular direction to the decision boundary, like, along this direction, as you go, any reason that the probability will make a very discrete jump, like from 25% to like 45% suddenly? Any reason to believe that? No reason, right? Probability is a slow increasing function, right? It's a slowly increasing function. The way you say it is that probabilities rise smoothly, slowly. The word for that is probability. More mathematically, you say probability Px is a differentiable function. It's a smooth function. Px, we will say, now we say based on our intuition, visual intuition, that Px is a continuous, smooth, continuous function. Curve. It's a smooth continuous curve. Now, what is the smooth continuous curve which doesn't have pointy edges that you can draw, which goes through, or which agrees to the two things? These are called the upper asymptotes. Upper, the word, I'm just throwing in the words, upper asymptote, and this is the lower asymptote. Means the value, if you go too far down, the value saturates at 0, isn't it? Saturation points. And so what is the one curve that you can draw? Can I go like this? Is this okay? No. As the distance increases, there is one more quality that I need to address. The closer I come to the decision boundary, the more the probability, right? If I'm going from negative to positive direction, right? You would agree that the closer I keep coming, probability will increase. There's no reason for probability to take a dip. Would you agree or not? Isn't it? That brings us to the last quality of this function. So we cannot have this. This is not possible. So I'll erase this, not this. It has to be, yes, the word is, it has to be a monotonically increasing function, a curve that is monotonically increasing. So what is the monotonically increasing function that you can draw? Well, this hardly looks monotonic in my, just imagine that if I was a better artist, I would have drawn something like, let's see. Does this look better, guys? I just making this fatter.
Yes, in lovely color.
Yes. Go ahead. Anil, go ahead.
No, there's a question.
Rantik.
Is that just the sigma function?
Yes, indeed. So all such functions which have, so now, so you just jump the gun a little bit. So guys, look at this. Logically, can you convince yourself that there is no other possibility? The shape of the function must look like this, isn't it? There is these functions. So what does this function looks like? There is an intuition. It turns out it looks like a stretched S, isn't it? If you take this S So imagine you take an S and you keep stretching it out. Does it begin to look like this? Right? And that is why this stretched S are called sigmoid. 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 Now, contrary to popular belief, there are actually many functions, many mathematical functions that have the shape. Many, many functions. All such functions are called sigmoid. So I give you a homework. Go discover as many sigmoids as you can by searching on the web and so forth. I will tell you one sigmoid, a couple of them we'll talk about today. One of them is, of course, the logistic function, because the name of the logistic regression, but there are many, right? There are at least half a dozen are well known, but there are many, right? So hold that thought in your mind. We'll take again a 5-minute break, and then we'll go ahead, Rantik.
Is there some other parameter you can message this?
Yes, we can, and we'll come to that. We come to that. In other words, how do you, not only that, you can translate it and you can flatten it, right? So there are 2 parameters that you have. Actually 3 parameters, because you can, even instead of rising up to 1, it could have been rising up to 2 in a different situation. Probability can, of course, only go to 1, right? So what is the amplitude? Where is the center? Where is it hitting 0.5 mark or mid mark? And is it very steeply rising or not? That's why this particular thing is almost like what is often called a 3-parameter model and things like that. So there is a lot going on here. We'll talk about that, right? Let's take a 5-minute break. Live stream on YouTube. Oh goodness, it is. So guys, this YouTube thingy, where is Anil? It might be a nuisance because every time I have to do this.
Yeah, I think YouTube really not required. I don't know.
Yeah. It's hard. It slows us down. Okay. All right. I'll do it. Or what I can do is not pause it. Just let it run all the time. Those of you who are remote, it slows us down. Okay. All right. I'll do it. Or what I. All right. What I will do now is restart where we left off. But before I do that, a couple of quick checks. So you guys are able to hear me in the classroom clearly because of the amplification. Those of you who are remote, are you able to hear me clearly?
Yes.
And
Yeah.
is the screen clearly visible? Is it legible what I'm writing?
Yes.
Yes.
That too is there. Thank you for the feedback. And are you able to see me clearly, or am I completely out of the screen, out of the camera?
No, we can see you, but if you could move it so that the doorway behind you is not in sight, that's a little
That would be
nicer.
better, isn't it? Hang on, let me take care of that.
Yeah.
Why not?
So, and another thing, can you lower the camera a little so we can see? We only see your head moving this side, that side.
Oh,
so when
my head bobbing up and down. Huh?
yeah, so if you could make it a little lower,
Yes,
so we
let me
can
do
see
that.
a bit
Let
of
me-
your little
I'm
lower.
trying all that.
Yeah, sometimes when you show the bowl examples, we're unable to see because when it's touching your hand, it doesn't cover your cover the bowls and stuff.
Oh, yeah. Oh, thank you. Thank you. Yes.
So whole example becomes an outlier.
Okay. How about now? Are you able to see me more clearly? And
Yes.
I think the thing that you're saying is turn you away from the door. Now you're not
Yes.
seeing the door, I hope.
No, we are not. It's good now.
Okay. And now let me see where I kept my writing pen. Here we go. All right, guys. So we will start. So this class of functions that have this shape of a stretched out S are called sigmoid functions, right? Now, there are many sigmoid functions, but amongst them, for classification, by far the most commonly used is the logistic function. Now, this word logistic is rather strange. Logistics, when we talk about, we think in terms of trucks and shipping and whatnot, isn't it? The logistic companies, they are the trains and the trucks and the shipping and moving things here and there, and the logistics of a project and so on thing. So what is a logistic function? It has its history, actually. Surprisingly, it is in I believe it had something to do with World War I. I forget what, but it has a military background, or maybe even before that, it has a military background. It was for the moving of food and other things to armies. In that context, it became famous. But it's a simple function, and I'll motivate it with a way that I hope you will get it easily. So let me go back to the simple decision boundary. So I will remove everything else, just draw the decision boundary. And I will say that for a point x, this is d of x, right? Simplified way. You realize that d, now let's look at the characteristic of this function. We know that when x very large, p of x, probability that it's a cherry is equal to 1, approximately. When dx is very large, negative, px is equal to 0. In other words, d probability associated with this, with d, let me just make a column here and tell me if this agrees with your intuition. Suppose I make a column here, d of x, and this is p of x. When this is infinity, d is infinity, what is px? 1. When d is minus infinity, what is p?
0.
0. When d is 0, what is p?
0.5.
A half. So now let's build through this intuition. And just to recap, the shape of it is like this, right? This is d of x. This is p of x. This direction is p of x, right? This is 1, right? This is 0. So with this intuition in mind, let's think of what you go. What you see is something very interesting. When you look from a mapping from D to, it's very simple actually. When you look at a function, think of a function, f, that maps from D to P, right, to probability. Literally, that is the P of D. So actually, let me see that this function P itself is mapping to this P of D. So it is mapping minus infinity to infinity. This interval, it is somehow able to map to 0 to 1. Isn't it, guys? It is able to squish an infinite thing. It is able to squish it down to 0 to 1 in such a way that you have a smooth rise up, isn't it, in the y direction. So let's think what function can do that. First of all, let's solve half the problem. And I'll motivate it to you. Suppose there is a function that goes from 0 to infinity. Right? Look at this interval, something that goes from 0 to infinity. Right? Now, anything that's defined in the domain 0 to infinity. What happens if you take the log of x? Log of x will go from where to where?
That's an open boundary on the side. Yes, you can't take you have to have an open boundary on the left.
Yeah, yes. It will go from minus infinity to infinity. In the asymptotic limit that it goes to 0, it's minus infinity, right? Log of x would go like this. Now this begins to look very promising, isn't it? Oh boy, maybe we need to somehow bring in a log of d somehow, isn't it? log of d. But there is a catch to it. D goes from 0 to infinity. Log will go from minus, so minus infinity. If you go like this direction, it is easy. If D is the log, it's like this, right? So you realize that whatever it is, this is the relationship. Now, how do you bring something that goes from 0 to infinity to 0 to 1? Suppose you could do one more step and you could go from 0 to 1, right? So this is the progression, guys. So imagine that what is it that we need to do to go from here to here? All you have to do is, suppose this was X, right? Or this was D. You know that you could do e to the D, it would go from 0 to infinity, isn't it? What is e to the minus infinity? 0. 0. So this step will take you there. What is that operation, e to the d? Let me write it here. What is that operation that takes 0 to infinity to 0 to 1? Yeah. So there is something very interesting, actually. You can go sort of backwards. You can say that if I want to go this direction, there is a common word that people use. They call it the odds. Suppose you have the probability of success is probability that your team is going to win a particular football or soccer or cricket or whatever it is. The probability is 0.7. What do you call the odds? Have you heard the word odds? The betting people don't use the word probability. They use the word odds. What is that? That is the probability of success over probability of failure, right? That is 0.7 over 1 minus 0.7. That is 7 over 3, isn't it? So they will say that there is more than twice the odds that your team will win. Are we together? You say that there is more than twice the odds that your team is going to win, right? So the word for odds is probability of an event, 1 minus probability of that event. Odds goes from what? Odds can be 0 to infinity. Odds is 0 to infinity. Do you see this, guys? Right? And so suppose your probability of it being strawberry is this, right? Then if you write the probability of it being strawberry, you convert it to odds. Odds will become what? 0 to infinity. You go this direction. Odds will take you here. And what takes you back to this? 0 to infinity. How do you convert to minus infinity to infinity? By taking the log of it. So log odds. Log odds will make it what? Log px 1 minus px. This will go from what range to what range now? This will go from minus infinity to infinity, isn't it? Do you see this, guys? I'm saying very simple thing. If probability goes from 0 to 1, odds goes 0 to infinity, we are halfway there. We just need to bring in minus infinity here because the distance goes from minus infinity to plus infinity, isn't it? I take the log of odds, and now I'm looking at one transformation of probability that has the same range as what? The distance function. Do you see this mathematical trick? It's very simple mathematical fact. So we say, what if, and so we are at this moment trying to invent a theory, right? We say, what if we posit that log odds of px, of the probability of x, which actually belongs to minus infinity, is basically proportional to, or why proportional? Let's just say it is the same as, is equal to the distance function. You can put a proportionality constant, but it doesn't matter, right? What you realize that this also goes from minus infinity to infinity. So what if we posit that this is true? We could do that, right? It would make sensible. Think about it. When you're really far in the positive direction, probability is close to 1, D is infinity, and log odds would also be infinity, isn't it? When you're literally D is minus infinity, right? Probability is 0. When probability is 0, log odds would be minus infinity. So it all seems to agree. And if you make this statement, you have essentially rediscovered, I should say, rediscovered logistic regression, right? In fact, this is logistic regression. This is logistic, actually, logistic equation. And if you take distance to be the D to be the distance from the decision boundary, in fact, this becomes regression equation. So let's write it down. Log of natural log, by the way, log is always natural. P x 1 minus P of x is equal to the distance from the decision boundary, dx. By the way, distance is often also written as z, right? Some literature often, this is not often, ML textbooks, right? So, but I'll call it this is actually, so now what is D? Now, this same equation, hold your thought 1 second. If I write it, if I do the inverse, guess what it will be? P 1 minus Px is equal to e to the D. Would you agree this is true? Right? And now let me make it into a more traditional form. I could say P of x is equal to, now if you just work out, so what you do is you add Px to the denominator. So it will become e to the dx, 1, then of course this is 1 plus e to the dx. Now divide numerator and denominator by e to the dx, it will become 1 over 1 plus e to the minus dx, right? Or also often written as, so probability of x is equal to 1 plus e to the minus dx, often also written as 1 plus e to the minus z. Are we together? It is often written as that. This is the logistic regression, but it solves one part of the problem. The second part we still have to work out is what in the world is D in terms of our, x1, x2 axes, right? The part that remains to be solved. But before we go there, guys, is this reasoning simple? You saw, we just made a theory. Hey, you know what? I need to convert probability into something, somehow do transformations to probability such that its values go from minus infinity to plus infinity. Why would I do that? Because D goes from minus infinity to plus infinity. Do you see that? If I could do that, then I could posit a theory. I would say this is the same as this, right? The transformation of the probability is log odds. So log odds is the same as the distance from the decision boundary, right? That is the basic idea. That is all there is to it, guys. So I'm giving you this intuition because I don't know how many textbooks actually explain this like this. Usually most machine learning textbooks posit this equation as a God-given fact. Logistic regression, this is the fact. Right. So I thought I would explain where all of this magic comes from. It's a very beautiful reasoning. It leaves one last topic there, distance function d of x. We still need to evaluate d of x. What is it? Isn't it? We haven't found dx. So we're going to do that the next time. But before I do that, guys, the odd logs business and probability, is that self-evident? Is that easy? Right? Now we'll just solve this last problem. So let's look at this. We have this, where goes our decision boundary? There we go. Here is our decision boundary. Decision boundary. Now, let us take an arbitrary point. Let's take a point Which point should I take? I'll take this point X, an arbitrary point X, right? And I will draw actually might as well draw this vector. I drew this vector, right? Actually, this point looks so orthonormal to the thing. I don't want to take this point. I take this back. Let me take another point where the geometry is more visible. Yeah, let me take a point. Let's take this as my point. Let me see if I am capable of drawing a, yay, I got my point right. Right. Now, what is the distance of this point from the decision boundary? What matters in reality is this. This distance is the real d of x, isn't it? Now, given the x vector, how do I get to the d of x? So one thing you realize, if I had, now we'll bring in a vector, which I will call the unit vector. For whatever mysterious reason, I will use the symbol beta. You don't have to use beta. You could use theta, unit, whatever. This is the unit vector. And these axes are x1 and x2 axis. I'm not using x5 because y in machine learning is reserved for the target variable. These are the two, feature space. So you would agree that this beta vector would be something like, it would go something like this. At any given point, it would be, so just draw a perpendicular bisector from here. You know, something that will hit at 90 degrees. This is 90 degrees. Let me call this distance, for whatever reason, let me just call this distance, give me a symbol, guys. What do you want to call this distance? Let me call this distance t, right? For no rhyme or reason. You could pick whatever you want, right? I'll do this. Let us take this unit. You realize that this line that perpendicularly hits is the line that is perpendicular, a vector that is in this direction, this vector is the vector orthogonal or perpendicular to the line. Do you see that? It is perpendicular to the line. Any doubts about it, guys? It's a very self-evident fact. Now, this unit vector, if I make it unit vector, means unit vector, so such that beta 1, beta 2, the components beta 1, beta 2 are such that beta dot beta is equal to 1. What do I mean by this? The unit vector dot product with itself is 1. The magnitude of the unit vector is 1. But what is the direction? The direction is what we are seeing here, beta hat, right? So now look at this vector and observe that if I just extend this line and I finish this curve, tell me one thing. What is the dot product? Let's ponder over this fact for a bit. What is the dot product of x dot beta unit vector? Right? What is the unit vector in this direction? What is the dot product of this x in the beta hat direction? It is, would you agree that that would be, again, let me use a different color. Would you agree that this is, isn't it? Dot product is nothing but the projection on the ground in the direction of beta, isn't it? So this red direction, this distance is that, all right? And so how much is dx? Would you agree? Now observe the relationship of dx to this entire thing. and you will observe something, the most remarkable and simple fact. It's a beautifully simple idea, guys. Huh? You will see that t plus dx is equal to x dot beta hat. Right? X, of course, being made up of x1 and x2 components. Would you agree, guys? Is this self-evident? Right? D plus T is the total length x dot beta. Anybody anyway has doubts? I can repeat it, but to me, I hope I've made it very simple. Simple, right? Right. So if this is true, now see the magic, guys, and you'll be absolutely love it. So you would say that dx is equal to x dot beta minus t. Right? So now let's work it out. What is this? X is x1, x2, right? Dot product of, like, how do you do the dot product? Transpose, in matrix notation. Anyway, I'll just leave it to you. You guys know that the dot product of this would be beta 1, x1 plus beta 2, x2 minus t. This is the distance, isn't it? T being the distance of the line from the origin, the shortest path, shortest distance of the line from any point, basically the orthogonal distance of the line from the origin. This, now you notice that these are all betas. Suppose we call this, by definition, we call this to be, by definition, beta naught. Then what does this equation become? This equation becomes beta naught plus beta 1 x1 plus beta 2 x2. Feels like magic, isn't it? Simple, very simple equation. That's all it is. So what we are saying is that the distance function is basically saying that it is given, distance from the decision boundary of any point is given by this. We just need to know the orthonormal vector, and we need to know the distance of the line from the this origin. Now you say, wait a minute. Why in the world this orthonormal business? We are all taught that equation of a line is mx plus b, isn't it? Why this strange way of writing it? So the thing is, we can of course reformulate it in terms of mx plus b and so on and so forth. We don't do that. Here's a reason why. See, a line is given by mx plus b, but when it comes to a plane where m is the slope, but when it is a plane or a hyperplane of higher dimension, now what? But you would agree that even if it is a plane or a hyperplane, still a vector, orthonormal vector, captures a hyperplane of any dimensions. It is a more general idea, isn't it? A hyperplane, an orthonormal vector to a hyperplane, along with the distance of the hyperplane from the origin, these two things will uniquely quantify a hyperplane in any dimensions. Right? It's very easy and geometric to state it like that. That is why actually in much of mathematics, except of course high school, you always call a plane, you identify a plane by its orthonormal vector. Here we call beta hat, but people call it u hat or whatever it is. The n hat, normal vector, orthonormal vector, and the distance from the origin. If you don't give the distance from the origin, there will be infinitely many planes parallel to each other, isn't it? But the moment you fix the distance from the origin, even it will just collapse it down to only one possible plane now, right? And if you only give the distance from the origin, there can again be infinitely many planes tilted at different angles, which would still be at the same distance from the origin, right? You can imagine a unit circle or a circle of that distance, and all tangents to that circle would be a plane that is at distance from the origin, right? So but when you give both the distance function, the origin distance and the orthonormal vector, you can quantify a hyperplane. And now you think of regression. We now bring it to machine learning. We are doing machine learning with many features, isn't it? So we are actually searching for a decision boundary in a feature space, in a data space, which is of arbitrary many dimensions, p-dimensional space. So, and we are searching for the hyperplane that separates the decision boundary as the hyperplane. So it is best to quantify that hyperplane using the orthonormal vector and this. And so let us summarize all this. If D is this, then you agree, let's plug it into our probability equation. Remember, we said probability of it being a cherry is equal to, or can I write it in a more formal language rather than the subscripts and so forth? Let me say probability of cherry given X at a point X in the feature space. X is a point in the feature space is equal to, remember, we did that 1 plus e to the minus dx. This is where we were last, isn't it? And that is equal to 1 plus e to the minus beta naught plus beta 1, right? Minus beta naught plus beta 1 x1 plus beta p xp, right? D, whatever. Let me just say beta n dimension. Suppose you have n features. Do you see this equation? Now, what happens is in your textbooks, you close the bracket. What is that? Oh, sorry. Yeah. Enclose in the bracket. You're right. So in your book, you typically see it in a more abbreviated form. People often write it just as px. Though even though it's a conditioned probability, they just sort of write it as 1 plus e to the minus beta naught minus beta 1 x1, right? Minus beta 2 x2. And so forth, right? And what this probability looks like, of course, we know that this is a sigmoid. It has a sigmoid shape. So what happens is that it has a shape like this. Asymptote 1, asymptote 0, right? D is equal to, this is where X probability is given as. Are we together? This is how you say it. So now there is a bit of abuse of notation. They will often call, people often call this the sigmoid function. But this is actually wrong, even though books call it. Sigmoid is a whole class of S-shaped functions. There are many. This is specifically the logistic function. What you just discovered is the logistic function. And it is everywhere, guys, this logistic function and sigmoid functions. In some form or the other, any one of the sigmoid functions, they dominate nature, right? If you look at in some sense, we think the fact that I'm talking, we are exchanging ideas, we are thinking, our nerves are firing. The firing of the nerve across the synapses, if you look at the electrical potential, the sodium-potassium balance rising, what is the shape of the activation? It is the sigmoid, right? If you look at a transistor firing, it is the sigmoid, right? It is shaped like the sigmoid. If you look at the population growth, suppose you take everywhere you look at the population growth in an ecosystem. Suppose there's a lot of resources and you have just two people, one couple there. They create and so on and so forth. And they have children, some children died, and so they have so forth. They have more children and so forth. At the end of it, what happens? The population is limited by the total amount of resources available, isn't it? Because after sufficiently high population, people will have just enough to survive, right? And population will start saturating, right? So population growth has a sigmoid structure. Wherever you look, you'll find sigmoids in nature. Logistic is by far one of the most commonly used sigmoids to model such behavior, population dynamics, and many, many things. And in fact, it is this is the logistic regression. What I just taught you is logistic regression. Are we together? So you take data and then you do that. Now the question comes, well, that is fine, but what is the loss function? How do you optimize? How do you find the decision boundary? How do you find the best beta naught, beta 1? So one may be tempted to say, well, we all know the sum squared error, right? The trouble is we don't have the notion of residual. It's not the gap. Remember, it's the confusion matrix, that matrix in which how well the child was able to tell the cows and the ducks, right? let's go back to our cows and ducks. You don't have the notion of it is wrong by this much. What you are wrong by, suppose you predict a probability of it being a cow, and it was a cow. So what is the ground truth? 100% sure it's a cow. You predicted that it is 70% it's a cow. Now your probability, because you're predicting a probability now. So you can't look at the gap between 0.7 and 1 and try to square that. There is a reason for it. But the reason for that has to do with something called Emily, right? There's a word in, there's a whole thing, concept called MLE. But if I were to choose to be mischievous, let's call her Emily, right? So we will all become friends with Emily after lunch, right? I notice it is 1 o'clock, so I will let you folks go. So Emily, we may do today, or we may do perhaps next time, why we don't take, what is the nature of the loss function? We have a choice, guys. We can take a short break and continue for 1 more hour, but that will really push out your lunch. Or we can do lunch and then do this, but we also have a lot of lab. Or we can do lunch and come back and do the labs only, because we have a lot of labs, and push this to next, the Emily part, the loss function part, to next week. What would you like? Do you think this is enough theory for today? That is it. Then that will bring me to Emily. Loss function is Emily based. Any feedback from those of you who are remote? Are you in for more theory?
I think we should do lab, and then we can do the Emily next week.
Next week. Okay. Any other voice? That's a good feedback, Sanjeev. Any other feedback? Anybody who wants to have Emily today? Nobody.
So why are you trying to do the Emily now?
Because it would close the topic of classifiers, end-to-end thing. That's it. But it's a long journey. I think we should stop here. It will take more than an hour. It will easily eat us. Yeah. No, I don't want to do only of theory. There's a lot of labs. We don't want to fall behind on labs. Today is a very, very long lab. Very long lab.
Switch to lab.
Let's switch to lab in the afternoon. All right, guys. So we will do the question. What Sachin is asking is, in this particular logistic function, what are the degrees of freedom? Like what changes the shape of the sigmoid of the logistic function? So the answer to that is quite simple. The beta naught controls whether, see, there are beta naught and beta 1. They control whether the sigmoid is like this or whether the sigmoid is like this in general. They control the shift typically. And beta 1 and beta, the other thing they control is whether the sigmoid is like this or whether the sigmoid is smooth, right? So these two factors, they control that, right? Then the one parameter that we don't need to worry about is the amplitude is fixed at 1. Yes. But if the amplitude also has to change, right, then it becomes a 3-parameter model, which we don't show here.
Because I thought it was the curve also, it becomes like this, right? Like
yeah, that is it. So you control with this, right. Beta naught, beta 1, right? So with these parameters, you can control how strongly it goes up and down.
But that's with the logistic, but the family of sigmoids will control even the angle at that curve, right? No.
See, the families are all very similar. So I'll give you an example. So let me just say there are 2 things. One is that, see, am I going like this or am I going like this?
Correct.
To this? Right. There is a word for this. They're very, what is for example, I deal with education. Yeah? So one of the questions we ask, so let me tell you something about one more location where these functions are used. It is called item response theory. So see, when you ask in a test people questions, the most obvious way to grade is to each question give 1 mark. If they answer the question correctly, 1 mark, right? So it's some, and you know that that is not true. Some questions are harder than others. Giving only 1 mark per question is not good. In our quiz, I tend to do that, but it's not good. So that reminds me of a king in India. There's a saying, Andher Nagri Chaupat Raja, Takeser Bhaja, Takeser Khaja, right? Means there was an ignorant king in whose kingdom everything was priced the same. Simple food and delicacies were all one rupee each. Yeah. So it is like that. What you want is some questions are harder. You need to give more weightage to that. So then the next step of evolution is, you notice people do, professors do in the exam, they will give, or teachers do, they will give more marks to harder questions and less marks to easier questions. But then the question is, how did they determine that? It is their gut check. You know that it's not reliable. Sometimes a 5-mark question will be easy and a 2-mark question will be hard. They get it right. So the thing is, how do you make sure that questions are truly a differentiator or ability to tell a person's talent, right? And so the answer to that is, what you do is, if you say that the ability, right? Ability is, this is the ability score, the actual ability on that particular thing, let's say calculus or something like that, ability at calculus. I'm just taking it, right? And you plot it against the probability that the person will answer it. So you know that at high ability, the person should be able to answer it. At low ability, the person should not be able to answer it. 0, right? So you want a curve that goes like this. But what happens is that a badly designed question will take like this. But a well-designed question will have this. In other words, between not having an ability and having an ability, right, the probability rises very fast. So in other words, if you did answer this question, right, the people who did answer this question, they all certainly have at least this minimum amount of ability, right? Very quickly it can tell. So these things are literally controlled by your beta naught beta 1s itself. But a separate question is, why did I use the logistic function? Here I use logistic. So I'll jump the gun, I'll tell you a solution. There are many other functions that you could use. One of them is so there's the logit, there is the posit, right? Well, you know what, I shouldn't say that, because then you won't go and discover the other sigmoids. Right? But when you discover the sigmoids, yes, you could do that. One of the reasons people don't like to use some of those other things is not because you can't. Logistic is famous because of some very simple reason. As you will see, if you take this function, logistic function, it has some beautiful mathematical properties. Amongst its good properties is the derivative of logit, right? dp dx is actually p1 minus p. Right. And other sigmoids also, some other sigmoids also. Well, I'm now tempted to tell you all the answers, which I'm not going to, because this is your homework. Let me erase this also, because this derivation too was your homework at some point. So there are error functions and other things, which also have exactly the same shape. But in a error function is, let me get the cat out of the bag for one of them, only one of them. Error function is related to sigmoid. Sorry, the bell curve. Yeah. The bell curve has how many parameters? Mu and sigma. Yeah. Do you see how these things develop, right? Now, there are many more sigmoids I won't tell you about. Go and find it out. Let's take lunch. Right? Because I'm going to announce a homework, which is literally for you to go discover. I mean, I have announced. Go discover all the sigmoids and observe their properties, right? So that is that. Do that.